We are interested in introducing mobile robots into the collaborative assembly process. However, this poses unique challenges for ensuring safe and efficient collaboration.
Current human-robot work cell requires robot to cease operation completely when a human enters the shared region. And today's industrial robots do not explicitly model or adapt to the behavior of the human. Here we present a human-aware robotic system that explicitly models and adapts to its human collaborators by predicting human motion and planning in time.
Space sharing co-navigation in manufacturing environments requires predictions across a wide range of time horizons. Short-term predictions are needed for collision avoidance, while long-term predictions are important for efficient sharing of the workspace. To accommodate this requirement, we use the multiple predictor system. This data-driven approach combines several complementary prediction methods to decide which of these predictors should be used for each time horizon.
Once the robot has both short-term and long-term predictions of human motion, it generates its motion with explicit modeling of time using the safe interval path planner. By representing time, the robot can autonomously decide when to wait, yield, and adapt to humans. We use a UR10 robot mounted on an industrial linear axis unit to implement our system. To the best of our knowledge, our human-aware robotic system is the first to integrate prediction and planning for operations in automotive final assembly. We demonstrate our system in a BMW test environment. In these demonstrations, the robot delivers parts from the depot to the workstation, while the human performs tasks in the shared environment. The human could select any motion corresponding to a predefined set of tasks.
First, we examine this scenario when using the baseline method, which emulates the behavior of standard safety systems in factories today. As the human enters the shared region, the robot is stopped. The human associate arrives at the depot, with the robot stopped nearby. Once the human leaves the shared region, the robot resumes its task. While safe, due to the large amount of time the robot is stopped, this mode does not allow for efficient space sharing. Next, we examine the same scenario, but using our approach of combining prediction with planning in time. Here, we see that, as we receive predictions that the human will approach the depot, the planner commands the robot to make way for the human. Now, the human reaches the depot with the robot waiting at a safe distance. Once the system receives predictions indicating the human is leaving the shared workspace, the planner commands the robot to resume its task. This anticipatory behavior was derived automatically from applying our approach.
We also evaluated our system in simulation of a factory environment. By interleaving prediction, planning, and execution, our human-aware system resulted in statistically significant improvements in measures of both safety and task efficiency.
For more details, we invite you to read our paper and join us at the interactive session.